In the previous couple of videos, we learned this method, this multi-step method, for figuring out what the graph of a polynomial looks like when that polynomial is given in its unfactored form. And I kind of picked on one example and sort of beat it to death, did the different steps out of order and taught some different techniques with it, and then sort of wrapped things up by doing all the steps in order to get an idea of what we're doing. But what I thought might be useful is just some repetition. All the different steps that you should expect to see, like if you're taking a test on this kind of stuff, but with different polynomials. So not just this same polynomial that we used a few times, but for example, x cubed plus 9x squared minus 12x minus 20. What would you do if you were given this unfactored polynomial and wanted to come up with its graph? Well, in our class, what I would ask you to do is first list all the possible rational roots of this polynomial. And what you need to know about the possible rational roots is they're always of the form plus or minus a factor of the constant term divided by a factor of the leading coefficient. So in this case, the constant term is 20 and the leading coefficient is a 1. And the factors of 20 are 1, 2, 4, 5, 10, and 20. And the factors of 1 are just 1. So I take any of these numbers up top and divide it by 1 to just get the possible rational roots are either positive or negative. 1, 2, 4, 5, 10, and 20. 12 different possibilities for the rational roots of this specific polynomial. But they're not all roots of this polynomial. This polynomial has at most 3 roots. So which of these 12 numbers are actually roots? Well, the idea now is to start testing them until you find one that works. So maybe the most logical place to start is by testing positive 1. So since f of x is x cubed plus 9x squared minus 12x minus 20, we can evaluate f of 1 pretty easily by just changing all the x's into 1s. We'd get 1 plus 9 minus 12 minus 20. And I don't know what that's equal to, but I can tell it's not going to be equal to 0 because I have negative 32 here and not nearly as many positive here. So this does not equal 0, so this doesn't work. But maybe f of negative 1 would yield a better result. Let's see what happens. Negative 1 cubed is negative 1. Negative 1 squared is positive 1. Plus 9 more gives me 9. Negative 12 times negative 1 is positive 12. And then I got minus 20. On the positive side, I got 21. On the negative side, I got negative 21. This is equal to 0. When I put negative 1 into this machine, 0 comes out. So negative 1 is a root of this polynomial. Because negative 1 is a root of the polynomial, x plus 1 is a factor of the polynomial. So this polynomial up here can be rewritten as x plus 1 times something. I want to know what that something is. To figure out what that something is, I can do polynomial long division. I can take this x plus 1 and divide it into x cubed plus 9x squared minus 12x minus 20. And because x plus 1 is a factor, which I know because negative 1 is a root, when I do this polynomial long division, I'm going to get 0 as a remainder, a nice built-in check. So how do I do my polynomial long division? Well, I stare at this thing and want to get rid of the leftmost term. So I got to write something up top. It'll be an x squared in this case, so that when I take that something and multiply it by x plus 1 and write that product down here, x squared times x plus 1 is x cubed plus x squared. And then subtract that product from the polynomial, I get rid of my first column. So x cubed minus x cubed is just 0. 9x squared minus 1x squared leaves me with 8x squared. And then I bring down the negative 12x, and I repeat that process. It's the exact same steps, except now I'm trying to get rid of this 8x squared, so I'm going to toss an 8x up here. Why 8x? Because 8x times x plus 1 gives me 8x squared plus 8x, and now when I subtract, this 8x squared goes away. Be a little bit careful over here. It'd be really easy to call this negative 4x, but it's not, because you have negative 12 of these x's minus 8 more of these x's, so you have negative 20x after you do the subtraction. We then bring down the negative 20 and try to get rid of this negative 20x. To do so, you toss a negative 20 up top. Negative 20 times x plus 1 is negative 20x minus 20. I subtract, and sure enough, I end up with 0 remainder, what I was expecting to get, because I knew x plus 1 was a factor of this polynomial. What that tells me is that this polynomial can be rewritten as x plus 1 times x squared plus 8x minus 20. I've rewritten this third degree polynomial as the product of a linear term and a second degree polynomial, which is a good place to be in because second degree polynomials are the types we know how to factor. So we stare at this second degree polynomial, and if it's going to factor, I need to find two numbers that multiply to give me negative 20 and add to give me positive 8. Let's see, I think positive 10 and negative 2 will work. So I got x plus 10 and x minus 2 as the factored form of this second degree polynomial. So the product of these three terms is equal to this polynomial. I've changed from the unfactored form to the factored form. Now that I have the factored form, I can come up with the graph pretty easily. I didn't really set up the scale here very well to be able to draw this, so maybe I'll rescale things. Let's call this, I don't know, 3, 6, 9, and 12 maybe. And maybe instead of 5, I'll make this 10 and this 20, and therefore this would be negative 10 and negative 20 would be somewhere down here. Now that I've rescaled things, I think I can sketch this polynomial. Let's see, I know that its y-intercept is negative 20 based on this negative 20 right here. So I'll put a dot down here. I know that its x-intercepts are at negative 1, negative 10, and positive 2. I can just look at the factored form and get all that information. So negative 10 is somewhere over here, negative 1 would be somewhere over here, and positive 2 would be somewhere over here. The multiplicity of each of those roots is just 1, and the end behavior from looking at the leading term is this polynomial is going to go up when it goes to the right and down when it goes to the left. So if I connect the dots, I end up with the graph that looks, loosely speaking, like this. Good enough. It doesn't have to be exact. In fact, there's a lot of characteristics of this graph that we don't yet know because we haven't taken calculus. But we have the x-intercepts correct, the y-intercept correct, the end behavior correct. We're calling that good enough. In case that was a little bit too fast or if you need more practice, let's do it again. Here's another polynomial, 6x cubed minus 13x squared plus x plus 2. First step is to list all your possible rational roots. To figure out our possible rational roots, we take the constant term, which is 2, and then we take the leading coefficient, which is 6, and we find the factors of those two numbers. So the factors of 2 are just 1 and 2, and the factors of 6 are 1, 2, 3, and 6. And we take either of these two numbers and divide them by any of these four numbers. So this 1 divided by this 1 gives me 1. This 2 divided by this 1 gives me 2. This 1 divided by this 2 gives me 1/2. This 2 divided by 2 gives me 1, but that's already on my list. This 1 divided by 3 gives me 1/3. This 2 divided by 3 gives me 2/3. This 1 divided by 6 gives me 1/6. And finally, this 2 divided by 6 gives me 2/6, which is equal to 1/3, which is already on my list. So for my possible rational roots, I have these 12 numbers, the 6 numbers written that can all be plus or minus. My next step is to find one of these 12 numbers that's an actual root of this polynomial. And this step can be kind of tedious. So typically what I do on a quiz is I tell you that value. I say, test the root at, I don't know, -1 to show that it's a root of this polynomial. I'll tell you which one to check so you don't have to just test them blindly. But in this case, we're not told which one to check. So if we call this polynomial f of x, we just need to start plugging these in, evaluate things like f of 1 or f of -1 or f of 2 and so on. Where should I start? Well, you might be able to just look at this and tell that 1's not going to work. Because when I plug in 1, the value of the coefficient will be the value of the term, this -13 will be kind of too big, loosely speaking, for me to get back to 0 by just looking at a 6, a 1, and a 2. Whether things are negative or positive, I don't think 1 is going to work. And I sure don't want to plug in any of these fractions. That sounds miserable. So I should probably mess with either 2 or -2. To figure out which one you should do first, if you think about -2, -2 squared will be a positive number. So this negative times a positive will be negative. But -2 cubed will be a negative number. And the positive times the negative will also be negative. So this will be negative, and this will be negative, and this will be negative, and this will be positive, but not nearly big enough to get me back at 0. So I don't think -2 would be a good idea to check. Maybe we check f of 2 and hope we kind of get lucky there. Let's see, if I change all the x's into 2's, since 2 cubed is 8, I would have 6 times 8 here, minus 13 times 2 squared is 4, plus 2 more. The arithmetic's a little bit annoying, but 8 times 6 is 48, and -13 times 4 is -52. So maybe you can kind of see how this is going to work out. If I take the positive side, I got 52, and if I look at the negative side, I have -52. I think when I put 2 into this machine, 0 comes out. So 2 is an actual root of this polynomial, not just a possible rational root. To find the rest of the rational roots, I want to do polynomial long division. To do polynomial long division, I need to know one of the factors. Since I have one of the roots, I have one of the factors. If 2 is a root, that means x minus 2 must be a factor. So I can do polynomial long division with x minus 2, and 6x cubed minus 13x squared plus x plus 2. and I should expect to get a remainder of 0. Polynomial long division will be a little bit tricky this time because of the negative signs floating around. I don't know that the process is any harder than what we did in previous examples, but it's at least easier to make a mistake. So we'll be really careful when we go through. Maybe first you'd put a 6x squared up top because your goal is to get rid of this 6x cubed, and you recognize that with the 6x squared here, 6x squared times x minus 2 will give you a 6x cubed. It'll also give you a negative 12x squared. The next step in my algorithm is to subtract this second row from the first row, and when I do that, this first column goes away. That's good. The second column, it's a little bit tricky. Negative 13 minus negative 12 is the same as negative 13 plus 12. And negative 13 plus 12 is negative 1. So negative 13x squared minus negative 12x squared is negative 1x squared, or just negative x squared if you want to write it that way. I then bring down the positive x, and I repeat this process. I want to get rid of the negative 1x squared here, so I better put a negative 1x up top. Negative 1x times x gives me the negative 1x squared that I'm looking for. Negative 1x times negative 2 gives me positive 2x, and I subtract. Again, I got to be really careful with the subtraction. This first column goes away completely. The second column, I got x minus 2x, so I got negative 1x. I bring down this 2, and I'm left with negative 1x plus 2. To get rid of the negative 1x, I toss a negative 1 up top, because negative 1 times x minus 2 is negative 1x plus 2. And now when I subtract, sure enough, I get 0 remainder. It looks like my original polynomial, which I'm calling f of x, can be rewritten as x minus 2 times 6x squared minus x minus 1. I'm not done. I still need to factor the quadratic term, this 6x squared minus x minus 1. That's a little bit harder to do because the leading coefficient is not a 1. There's a few different ways you can do that. Whatever method works best for you is totally fine. I find that most students kind of prefer this guess and check method, where they're like, well, a 3x here and a 2x here would do the trick. It would give me a 6x squared here. But now I got to pick out numbers that go here and here that multiply to negative 1. And if I were to FOIL everything back out, leave me with a negative 1x. So let's see, to get a product of negative 1, I need one of these to be positive 1 and one to be negative 1. And if I put the negative 1 over on this side and the positive 1 over on this side, then when I FOIL things back out, I get negative 3x and positive 2x, which net out to the negative 1x that I'm looking for right here. What I'm saying is 6x squared minus x minus 1 can be rewritten as 3x plus 1 times 2x minus 1. Now that I have the factored form, I'm essentially done. I could sketch the graph of this polynomial. Maybe we start with the low-hanging fruit. We talk about the y-intercept. It looks like the y-intercept is 2 for the constant term here. So my graph's going to go through this point right here. Then I look for the roots. From this factor at x minus 2, I get a root at 2. From this factor of 3x plus 1, I get a root at negative 1/3. If you have a hard time seeing that, take the 3x plus 1 and set it equal to 0, and then solve. Subtract 1 from both sides of the equation and divide by 3, and you get that negative 1/3. By the same logic, this factor at 2x minus 1 leads to a root at positive 1/2. So I'll put that right here in my picture. All these roots have a multiplicity of 1, so they'll be easy enough to sketch. The only thing left to consider is the end behavior. I can get the end behavior by looking at the leading term in the unfactored form of this polynomial. Because it's third degree, it's going to go in different directions as it goes left and right. And because the leading coefficient is positive, it's going to go up when it goes to the right. So therefore, it must go down when it goes to the left. I connect the dots as best as I can, giving me a graph that looks more or less like this. It's not exactly what the graph of 6x cubed minus 13x squared plus x plus 2 looks like, but it does capture the important characteristics. Important for the purposes of our class is the y-intercept, the x-intercepts, the multiplicity of those x-intercepts, and the end behavior. You might notice that so far we've only dealt with third degree polynomials, and that's intentional. When you start dealing with fourth degree polynomials, things get really hard. Maybe that's a misnomer. It's not that they get hard, they get really tedious, they get really long. But we can do this exact same process even if we have a fourth degree polynomial. So what I want to do is show you how to do it with the fourth degree polynomial. But in order to keep the length of these videos as short as possible, maybe I'll save this for the next video.